So this is another important article about entity linking, which is called Low Resource Recognition and Linking of Biomedical Concepts from a Large Ontology. It is written in 2021. But I think we should reduce the redundancy of this algorithm. Many things in this algorithm are redundant. I mean, in terms of dependent variable, independent variable, we should reduce the number of dependent variable, and otherwise it produces spurious correlations, I think. And this article is also interesting in 2018, end-to-end, which I will explain it. And I will also explain this one. But for now, I will focus on this important article about low resource recognition. So semantic indexes, as you know, UML concept in biomedical text, we always use this UMLS knowledge graph, that we have a concept, we have lots of concepts. And so always we try to ground our work to these things in order to have a unified and global framework that can be evaluated or measured with other works of researchers in this area. So that's why UMLS is very important. So semantic indexes that record the scientific entities, like this one, this protein, or Nipah virus, and a drug, this one. So these are mentioned in each paper are a core component of tools for literature, search and exploration. These indexes account for the ambiguity in the way entities are mentioned and map them into controlled ontology. For example, UMLS concepts that I said. So UMLS concept start with C. For example, C11, this is one concept, this is another concept. So this allows users to access information more easily without needing to query for a wide variety of aliases, spelling of an entity name, and etc. So to build such a semantic index, entity mentions must be recognized and linked in the text of scientific papers. So this is the goal of entity link. So these tags are widely used. We have done it for Wikipedia resources, but for the domain of biomedical text, it is still in its infancy. So UMLS, using mesh API, we can connect to biomedical literature and get, for example, the hierarchy, the graph, the tree structure, some definitions, also not precise, but it's good. And when we have a PubMed article, we try to index with mesh so that we understand, we can classify this article. Even we can search this article among millions of articles, now billions of articles. And another important thing is Go. Using this API, you connect to genome annotations. These are the only articles. I'm not familiar with the rest of them, but this one is also important for clinical repositories, SNOMED. And so UMLS consists of concepts. As I said, we have 1 million biomedical concepts. It's a huge knowledge graph. And we have semantic networks. For example, what is the relationship between them? And between we have type as well. So we have groups, and then we have, each one has its own. I will explain. And so you have UMLS semantic types. It could be organisms, it could be biological functions. These are semantic types. So we have two main categories. Your categories could either be entity or event. As I said, your category could be either entity or event. We put them in, they are in the root of the graph. And for example, a type of, for example, for event, for this, let's call it category, and these are categories. We have different types, semantic types. Is, for example, if it is activity, then it is either machine activity, occupation activity, behavior, and it is occupation activity is research activity or healthcare activity. And UMLS, if the root is root, then you have disorders, chemical, drugs, anatomy. So a portion of the UMLS semantic network is relations, which is very important. Because it connects, for example, it says this biological function is process of this organism. So this is an example of biomedical entity linking that you are familiar with. We have a text. So here is mention, and for this mention, we rank it, for example, this entity, these are, we rank these articles, and we suddenly know this is the gold one, so we have done it wrongly. So what are the challenges? The domain of biomedical research papers, however, has a relative lack of training data resources. While datasets for some small ontologies have been widely studied, chemicals and diseases, the more useful comprehensive ontologies are large, lack descriptive text defining most entities, and labeled data can cover only a small portion of ontology. At the same time, ontologies such as UMLS do contain useful information, supplementing entity names with aliases, acronyms, entity types. For example, this is a very important information. This is different types of names, so this is useful. So in this paper, they describe a new model for detection of mentions and linking them to concepts in an ontology of fine-grained types that is designed to operate in a low-resource setting. So it's a low coverage of the ontology in the training data and with no descriptions for concepts or their types. So the final stage then predicts which of the link spans, because we assume that there are many different spans. We test all of them, and at the final stage it predicts which of the link spans are the actual span, are the actual mentions in the document. And they use multi-attention network to provide dynamic cross-attention between mentions and concepts. So first they do candidate generation, then span linking, and then span selection. So given a document, a sequence of tokens, and a knowledge base, we consider two tasks. Entity recognition and linking requires predicting a set of mentioned entity pairs. So UMLS is an ontology of biomedical concepts that are named fine-grained types. For convenience, we shall refer to these concepts as entities. So we connect mentions to entities, we link them. The candidate mention spans, and the names are not unique. It may link to several names could be linked to one entities. And here we are creating a similarity between a mention and each name. And we use cosine similarity for that. But we use both word and character level because we are using this TF-IDF vectors and we assume that there are n-grams. So finally we get the lexical matcher, which is this one. So for any mention, we have this vector, which gets sorted on decreasing, and So after that, we have span linking. We use classification token and then your C of M, and then separator, and then entity description instead of entity description, and then separator again. And finally, we use this feed forward network that has some inputs. One of them is the output of this input. So this one is, and then we use pooling as well. So the final thing becomes B sub L. But we have other information that we can use as well. For example, embedding of your type of entity, and we put those things in some bins for some reasons, and we have the lexical match score S sub E as well. And for link span selection, they say this is the score of mentioned entity, and that's probability. It's interesting that they put probability here as well as one of the inputs. So you see some redundancies because P itself is given a mention what is the probability of your entity. But so you see you can reduce the number of things or processes that you are doing. And finally, they use max margin loss because we want to be robust, so that we want to have a good margin. And our margin is always M in machine learning. M stands for margin. So if your mention an entity is ground truth, use this loss. Otherwise we use the maximum of this. So this is the process. First we use candidate spans, then matching, then embedding, then concept linking, and finally link span selection. Concepts in UMLS are named fine-grained types. Each concept is associated with a broader category called, as I said, semantic type. And UMLS provides each concept with a preferred primary name and some synonyms and acronyms. And there are 3 million concepts in UMLS in 2017. So these are ambiguous mention linking, because although the mention is the same, but this one is linked to another entity. This mention is linked to another entity. So there are some ambiguities. For zero shot, they use zero shot for evaluation only, not for training. For evaluation, they use a set of unique entities. And med mentions, as you know, 42% of unique entities mentioned are new. They haven't seen. So we evaluated performance of our model on this dimension by comparing its predictions of mentions of new entities against new entity mentions.